So after we have talked about the first case about indoor swimming pools where there was this collapsing of the ceiling, you can imagine after this very big accident, many other indoor swimming pools have been investigated by local governments, by cities, by authorities, to find out if these pools are safe, or if they are not safe, then they have to be shut down. So I give you another example, which at that time I myself investigated. It's the following indoor swimming pool in Kilchberg, nearby Zurich, and there it was running. Our task was, the order was the control of the steel hangers. You see now here the design in this image, it's a little bit different. You see here the building of the indoor pool, and then the top, this design of steel construction, and on this steel construction only one ceiling was attached. So not like in Uster 2 ceilings, here one ceiling. However, it has to be also attached. And it was already also the pool about 12 years running, 12 years old. And you see here the design, you see here these steel hangers. And there is inside the pool, you see there it was attached with some wooden, that it is not seen from down, the design, the construction. And then the steel hanger attached here on this very big steel construction, and on the top, which you see here. And there was, you even could walk here around. There was a layer of small stones and sand. And here I can already tell you there was highly corrosion attack. Now the mechanical loading again, it's like before on these kind of steel hangers, it's simply tension, it's merely static. There's no shaking, no fatigue, no changing load. Of course there is sometimes a little bit snow on the ceiling, but this is not so much the difference. Now we again, of course we think then later on also on the stress of these steel hangers, but in principle I already tell you the loading on each steel hanger, it was 11 tons on each of them. And but they had a very higher diameter compared to Uster. They were M30, so a diameter of 30 millimeters. Uster, you remember, was 10 millimeter. And now the main difference was also the construction, the material used. It was not an austenitic stainless steel, it was a very simple, also much cheaper ferritic pelletic steel. And this designation 8.8 is a German designation, I can tell you. It says that the ultimate tensile strength is 800 megapascal. And this 0.8 means 80% of the ultimate tensile strength is yield strength. So when we calculate this, is very easy. It's 640 megapascal. It's also a much stronger material compared to the austenitic stainless steel. But we come back to this later. Yes, this I told you already, there was already found a region of intensive corrosion attack. Okay, so when we have to control this, we have to make a decision what we are doing. And it was again about 200 of these steel hangers which supported this ceiling, and we had to make a selection. Of course, you cannot change and watch all the 200 ones. We said it was in the range of about 12 or 15 steel hangers, which has to be replaced. Of course, step by step, you remove one steel hanger and you put another inside. Remove the next one, and of course, you make also a selection of the different areas. And this is already, we asked then ourselves what kind of investigations we have to make. Because we have to be, this is very important, at the end absolutely sure in our conclusion if this indoor pool has to be shut down or it is open. is nothing between, and we have to be absolutely safe, because when we say we can leave it open, then we have to be sure that in the next 20 or 30 or 40 years of the lifetime of this indoor pool, it will not collapse, because it's only 12 years, and normally these kind of buildings have a lifetime of 50 years. So we have to make also a prediction for the next 40 years. So we have a lot of responsibility. So we have to work very carefully. The first thing what we have to do, of course, we have to check then talk about this corrosion attack, which we found here, if it's similar to that what we saw before, if there is of course any cracks inside. And to find this out, it's a very simple but a very effective test which we start at the beginning. It's so-called non-destructive testing. So we have the whole bar, the whole screw, which we see here, the steel hanger, and it was just put, for instance, there's different ways of non-destructive testing. One way is, for instance, you apply there a certain color on the material, and you go there under UV light, and in UV light you will see if there is some announcements of cracks, and there you can investigate very carefully. So it's very important, then you have an idea of the whole component and not partially. It's very important. The next step is also very important. Maybe there is some signs from non-destructive testing, some appearance, if there is a crack there, or maybe also in this region, then we selected some of these steel hangers and we performed with them directly tensile tests. Mechanical tests, a tensile test, but it's very important with a component, not any specimen from here out that tells you nothing. We have to make a mechanical tensile test with the whole component, and for this we have big enough machines available. Because it's clear with this mechanical tests on the component, they will tell us the result if the values for the ultimate tensile strengths, for the yield strengths are fulfilled or not. And the third part, of course, we have to watch also carefully by metallography to the microstructure. We watch carefully to the corrosion layer, what's going on there. But it's the third step, it's not at the beginning, because imagine when you make a metallography and you cut there somewhere inside, you then only check then a small area here. You have to know about everything. You cannot slice all this and then it's not enough information. So we have to start with this here first. Metallography, we will learn then more. And the fourth step, we have to know something a little bit about this corrosion layer, which we already see here, and it will be very important also for the prediction to make a chemical analysis by XRD or by microprobe analysis. This is important, these steps, and this you have to be carefully in mind. I also will ask these different steps in the examination. Now you see here these steel hangers, some of them were selected from the lab pool, M30, and everywhere you see more or less at the same spot this corrosive attack. And that one from the wading pool, a little bit smaller ones, M20 steel hangers, but again here in the upper middle part we see this kind of corrosion attack. And it's here fit inside here in this drawing, and you see it correlates quite good with this area which we have seen here before on the top. Now that is now at higher magnification, and I even have this component with me. Look at this here. It has a thickness of 30 millimeters, and it's heavily corroded, is it? And it looks really crazy and dangerous. And when you compare this, especially with this austenitic stainless steel, which we have investigated before, with the Uster case, from outside, it looks really heavily corroded, crazy, and we have to be afraid. But now that step is coming, and this is shown here, that we made here this cut inside of the material here where it was heavily corroded, and we see already our metallographic specimen. And in the metallographic specimen, this is the white part that is an iron underneath. And that part here, which we see here, this is our corrosion layer. Our corrosion layer. It's not equal, it's a little bit here higher. Now, that is the most important image. We compare this again with the Uster case. We have here this corroded layer, but do you see any crack? There is no crack. There is no crack inside in the material. For this, to watch for cracks is also very important that the base material, the iron, is not edged. You can edge it, then you see the microstructure, but without edging you would see much better if there is any crack. You see here a small crack in the oxide layer. That is even the reason why there is a little bit bigger. Come back to this later. But important, no cracks inside. And the cracks, they are the dangerous part we have to take into account. Okay, now oxide layer, no cracks, keep in mind. This is just to show you the microstructure of this 8.8 steel. It's a ferritic paralytic steel, and you even can judge a little bit the carbon content of the steel. You see here, this is all our paralytic parts here. You see here the stripes of the perlite, and between the white one, this is a ferrite. And you know the phase diagram of iron carbon, and when you think of the eutectoid, where is the eutectoid? The carbon where you have 100% perlite, it's at 0.8% carbon. So when we judge this, the amount of ferrite, I guess there is about in the range of 0.6 to 0.7% carbon inside. Okay, ferrite, perlite, microstructure. Now the next slide is very important. It shows you now the whole diameter of our steel hanger and this cut here. And you see here the inside, it's again just white. You see no cracks inside. That is our base material, and around you see the oxide layer. Around the oxide layer. And you see here the scale, it's 3 millimeter. So we can judge a little bit because it will be important now to calculate the stress in the rest of the diameter, because that oxide layer doesn't take over any load. So the stress will be higher because the diameter is reduced. The diameter, let us judge. When you watch at this, I think it's about here 1 millimeter, maybe here a little bit more. So totally we judge it's about in the diameter, the corrosion layer, maximum 2 millimeters, which will be reduced of the load-bearing area. Because again, the corrosion layer is just brittle, it falls apart, you can scratch it off, it's less. So in the next diagram, and this is also very important, this diagram you have to keep in mind, and I asked this also in the examination. You do not need the exact values, but it is the most important diagram here for this investigation. It shows the following. You see here now the stress. You see here the diameter. That's the original diameter is 30 millimeters. So the original thickness of our bar, which we see here, that bar. And you see something else before we come to the layer, that compared to the Uster case from before, this is our original stress in our steel hanger. It's in the range when we go to here to about, let me say, 160 megapascal. And you see here in this line, the yield strength, I told you that was 640 megapascal and the ultimate tensile strength 800. So we are very, very safe. We were in our design very far away from the critical amounts of the stress. Very far away. And due to the fact that it is so far away, you easily can calculate here because we have the diameter, we have the load on each steel hanger. I told you 11 tons. You can easily calculate then the stress, how it gets a little bit higher when there is less diameter available. Okay, look, when you come here, of course, when you have instead of 30, you have 18 millimeter diameter available, then the stress gets higher and higher. That's clear, it gets less. But in our case, where we have only a loss of about 2 millimeters, you can even say 3 millimeters, it's only a slight increase of the stress. So that seems to be quite safe, very safe. The question is now, can we already now finish our report and come to the conclusion that it is all safe? No. Why? As I told you, this is now a time scale of 12 years, this oxide layer. And then, again, the lifetime of this building is supposed to be 50 years. So this happened in 12 years. How do we know what's happening in the next 40 years? If it's just going up and up, and then maybe after another 20 years, it will be here. So we have to check. And we have to apply, it's now very important, our knowledge about corrosion of iron. This will corrosion of iron. Yeah, first this again the comparison, and then we come back here to the corrosion of iron. Look, very nice to see again the two cases. Here the Uster case, you remember that steel bar. From the outside it looks not that bad. All these small pits just, and the inside from the pit, the cracks, they are dangerous. It was totally cracked. And here, from the outside, it looks very crazy, very much heavily corroded. Then we make the microsection and we see here the corrosion layer, and underneath in the base material, no cracks. So here no cracks and here cracks. That's a big difference. And again, the story, this is a much cheaper material compared to that. Now, as I told you, we have to think about the mechanism of this oxide layer. The question came up if this oxide layer in the next 40 years will grow and grow, not here in this direction, of course, grow, and then the load-bearing area would get smaller and smaller. We will ask ourselves, what is the mechanism? The mechanism that this front of the oxide layer is going here inside needs that oxygen, 2 minus oxygen, has to diffuse here inside and then can make the reaction with iron and growing inside. However, our knowledge about oxidation of iron is the following. That is the different steps of iron oxidation. The first one, it starts with this iron and these OH groups, then the next one, iron oxygen, and the next one, iron 2O3, and the last one is iron 3O4. what do we know about iron 304? Iron 304 is very stable and it's very dense, and if this would be here, iron 304, then there is nearly no, or the diffusion rate of oxygen is extremely low. So it would take a long time, or even there's no oxygen diffusion possible, that the oxygen diffuses to here, that this layer is going here more and more inside. That means if we find this stable oxide with high density and low diffusion rate for oxygen, then it would be fine. And this we easily, of course, can measure. Just to show you, this is a backscatter electron image here, and in the same machine, in the microprobe analysis, we see here the distribution by mapping. That is for the backscatter thing. That is for iron, the distribution, sorry, and this is for chromium. Of course, there's chromium in the oxide layer, and also, of course, the oxide. That's oxygen. However, this just shows you a little bit of overview for precise measurement. What kind of tool, what kind of examination do we take there for exactly examination? We scratch away here from the oxide layer some material, bring it to the chemical laboratory, and they will tell us exactly what kind of composition. And you can already guess what we found. The oxide layer was a composition iron 304. So exactly that what we like to have here, what we also expect from our knowledge. When there is this dense oxide layer with a low diffusion coefficient, we should be safe. No growth anymore of the oxide layer inside. That's very important. Okay, we already can conclude. The construction and the material is safe. We have seen the construction, the design. We were very low in the static stress of these steel hangers, very far away. The material selected, it showed some corrosion, a corrosion layer, but no cracks. And again, the mechanical loading far below the yield point of the material. The material's loss due to corrosion is predictable. And the corrosion process, at the end, there are stable oxides formed. You can make this also in a test. There is this so-called parabolic growth of the oxide layer. And finally, we are nearly at the end, and to be very safe. But to be absolutely safe, and why not? Because we want to be 100% sure, there was following proposed to the order of this, the government, the authorities of this small town of Kilchberg. We told them to be sure periodically the next 2 to 3 years, and again maybe then another 3 to 4 years, not all of them like here now 12 or 15, 2 or 3 should be again checked, but of course not those who had been replaced, those who had been already then inside for about 12 plus 3 years, 15 years, and checked if this corrosion layer is stable, not going. Then we are absolutely safe. So no shutdown of the swimming pool and periodic control of the steel hangers. So all these investigations and our knowledge about especially corrosion, about corrosion of steel, of this ferritic steel, was important to come to a clear conclusion. And again here, the architect, the engineer, did the right job, even selected a material which is much cheaper compared to that austenitic steel, and also the design was good enough. It's no problem when this steel hanger has a little bit of bigger diameter, it's more safety, the price doesn't play any role. So we have here a nice example that everything was well, good. So again here, if you have any questions, you may contact me or have a telephone call. And again, at the end, I wish you a good time, especially good health, and we see us next week again. Thank you very much.